Scientists finally explain mysterious, impossible merger of two massive black holes. A detailed suite of simulations conducted by astrophysicists at the Flatiron Institute and their collaborators showed that magnetic fields can produce black holes with masses that were previously believed to be mostly unattainable. In 2023, astronomers recorded a dramatic cosmic event. Two unusually large black holes collided about 7 billion light-years from Earth, and their immense size and rapid rotation immediately raised questions. Objects with these characteristics were not expected to form in the universe. Researchers at the Flatiron Institute's Center for Computational Astrophysics, or CCA, working with international collaborators, have now identified a possible explanation for how these black holes were created and eventually merged. Their detailed simulations, which track the entire evolution of the system from the birth of the parent stars to their final collapse, revealed a crucial factor that earlier studies had missed: the influence of magnetic fields. No one has considered these systems the way we did. Previously, astronomers just took a shortcut and neglected the magnetic fields, says Odin Gottlieb, astrophysicist at the CCA and lead author of the new study on the work published in the Astrophysical Journal Letters. The puzzling mass gap problem. The 2023 collision, now labeled GW231123, was detected by the LIGO-Virgo-Cagra collaboration, which uses gravitational wave observatories to measure slight disturbances in space-time caused by massive cosmic movements. At first, scientists could not understand how such heavy and rapidly spinning black holes could have formed. Massive stars typically end their lives in explosive supernova events that can leave behind a black hole. However, stars within a certain mass range behave differently. They produce what is known as a pair instability supernova, a powerful explosion that completely destroys the star and leaves no remnant. As a result of these supernovae, we don't expect black holes to form between roughly 70 to 140 times the mass of the Sun. So it was puzzling to see black holes with masses inside this gap. One possibility is that black holes in this mass gap form when smaller black holes merge, creating a heavier one. But for GW231123, this explanation seemed unlikely. Black hole mergers are highly disruptive events that usually scramble the final black hole's rotation. Yet the black holes in this collision were spinning faster than any previously measured by LIGO, pulling the fabric of space-time with them at nearly the speed of light. The chances of two such massive, rapidly rotating black holes forming through typical mergers appeared extremely low, suggesting that another process must be responsible. Simulating the evolution of a giant star. Odin Gottlieb and his collaborators investigated by conducting two stages of computational simulations. They first simulated a giant star 250 times the mass of the Sun through the main stage of its life, from when it starts burning hydrogen to when it runs out and collapses in a supernova. By the time such a massive star had reached supernova stage, it had burned through enough fuel to slim down to just 150 times the Sun's mass, making it just above the mass gap and large enough to leave a black hole behind. A second set of more complex simulations, which accounted for magnetic fields, dealt with the aftermath of the supernova. The model started with the supernova remnants, a cloud of leftover stellar material laced with magnetic fields and a black hole at its center. Previously, astronomers assumed that the entire mass of the cloud would fall into the newborn black hole, making the black hole's final mass match that of the massive star. But the simulations showed something different. Magnetic fields changed the fate of collapsing stars. After a non-rotating star collapses to form a black hole, the cloud of leftover detritus quickly falls into the black hole. However, if the initial star was rapidly spinning, this cloud forms a spinning disk that causes the black hole to spin faster and faster as material falls into its abyss. If magnetic fields are present, they exert pressure on the disk of debris. This pressure is strong enough to eject some of the material away from the black hole at nearly the speed of light. These outflows ultimately reduce the bulk of material in the disk that eventually feeds into the black hole. The stronger the magnetic fields, the greater this effect. In extreme cases with very strong magnetic fields, up to half of the star's original mass can be ejected through the black hole's disk ejecta. In the case of the simulations, the magnetic fields ultimately created a final black hole in the mass gap. We found the presence of rotation and magnetic fields may fundamentally change the post-collapse evolution of the star, making black hole mass potentially significantly lower than the total mass of the collapsing star, Orna Gottlieb says. The results, Gottlieb says, suggest a connection between the mass of a black hole and how fast it spins. Strong magnetic fields can slow down a black hole and carry away some of the stellar mass, creating lighter and slower spinning black holes. Weaker fields allow heavier and faster spinning black holes. This suggests black holes may follow a pattern that ties their mass and spin together. While astronomers know of no other black hole systems on which this connection can be observationally tested, they hope future observations may find more such systems that could confirm this connection. The simulations also show that the formation of these types of black holes creates bursts of gamma rays, which might be observable. Looking for these gamma ray signatures would help confirm the proposed formation process and reveal how common these massive black holes might be in the universe. Ultimately, if such a connection is confirmed, it would help astronomers gain a deeper understanding of the fundamental physics of black holes. Reference: Spinning into the Gap, Direct Horizon Collapse as the Origin of GW 231123 by Orna Gottlieb, Brian D. Metzger, Danat Issa, Sean E. Lee, Mattia Renzo, and Maximiliano Isi. 10 November 2025, the Astrophysical Journal Letters.